Okay, we are, I believe, off to chapter 11 here, which is organic. And we're moving into the course part of the course where it's, not going to be pretty much any calculations in this part. It's going to be more sort of memorization, naming. We'll also talk about some reactions that occur. So that's what's on tap here. So let's start with sort of organic chemistry. Really, organic chemistry is really the study of carbon. That's usually the first sentence in every chemistry textbook or organic chemistry textbook. Is really the study of carbons. And pretty much most organic compounds are composed of essentially carbons attached to other carbons, and attached to those carbons some hydrogens. And every so often, we kind of swap out some hydrogens from other elements, and we get some different types of organic compounds that there are. Now, organic compounds are a lot of times going to be non-polar, or the basis of organic compounds are really non-polar. And again, that is really because of that basic bond between carbon and carbon, which is obviously a non-polar bond, as they have the same electronegativity, and also primarily bonding between carbon and hydrogen, which is also a non-polar bond based on electronegativity. So a lot of organic compounds are non-polar. There are, as we will see as we go through the different sort of organic compounds, there are certain ones that do become sort of polar in a sense, or have a part that is polar when we replace like carbon, hydrogen with some other bond. For example, at some point we will see this guy that has basically this OH group on there, which just like in bonding is a polar group, and it's kind of a negative positive situation happening there. So that's typically what you find in sort of organic compounds is the vast majority of the organic compound is basically made up of this non-polar part, but every so often there's little parts on there that can be polar. For example, those are alcohols. They're with the OH group, and they are polar because they have that OH group. They could do hydrogen bonding and are very polar in a lot of senses. So an organic compound is a compound made up of carbon and hydrogens mostly. And as I said, as we go through it, we'll substitute other elements in. Oxygen is very much found in a lot of organic compounds. Sulfur, nitrogen, and phosphorus, and the halogens as well also pop up. So group 7 on the periodic table. It's common in products such as gasoline, medicine, shampoos. I think we might have talked about earlier and talked maybe about solubility, but things like petroleum or gas is basically just nothing but a long chain of carbons and hydrogens basically together. Octane is 8 carbons basically, like when you put in your car. And again, it's just nothing but these carbons and hydrogens. The formulas of organic compounds are written with carbons first, followed by hydrogens, and then usually the other elements. And really that's because carbon and hydrogen does sort of make up the backbone of most organic compounds. So when you see a formula, oftentimes it's like, C2H4O, something written like that, with carbon and hydrogen sort of coming first. And then again, the other sort of elements would follow. So some properties of organic compounds, as I mentioned, pretty much is carbon and hydrogens along with oxygen, some of those other guys, nitrogens, and so forth. Those are all nonmetals. So what we're dealing with here are guys that have covalent bonds, which are sharing of electrons. So these guys have sharing of electrons. They usually will have very low melting points and boiling points, and are flammable and undergo combustion reactions. So like your Bunsen burner type reaction, a little bit of methane plus some oxygen, a little CO2 and water, not balanced, but that's basically our combustion reaction that we're talking about here. They are also typically not soluble in water. And I believe we talked about the idea of like dissolves like, and what we are dealing with in the case of water, which is polar, And pretty much organic guys, for the most part, are non-polar. Those guys really do not mix. So if you ever think about, again, like oil and water, oil will tend to float on top of the water in that particular case. In most cases, if you put sort of an organic guy and water in a test tube, it is typically the organic guy that ends up on top. The water, our aqueous part, really does end up there on the bottom. Thank you. Now, some differences between organic and inorganic compounds. Or inorganic compounds, things like salt, sodium chloride, they typically have very high melting points and boiling points, and that is because they are held together by that really strong electrostatic attraction, the positive negative attraction between ions. It's kind of like your super strongest attraction you could get. So they're held really, really together. And as we talked about sort of in the gas chapter, you could pretty much heat the heck out of it, and it really won't go into sort of the gas phase or anything like that. A lot of organic guys, which are non-polar, are basically using dispersion forces. And if you remember, dispersion forces are really those weak intermolecular forces. So what happens is it doesn't take a lot for them to sort of go into the gas phase. And they're basically held together by these intermolecular forces. And these intermolecular forces are much weaker than intramolecular forces, which is what holds together an ionic compound. So when you heat it or whatever it may be, you know, this force breaks apart a lot easier. A lot of the very sort of simplest organic compounds, things like methane, propane, butane, those are all gases that you may be familiar with. And a lot of organic compounds are said to be very volatile, which means they will go into the gas phase really easily. So a lot of times if you ever take a real organic course, they usually stick you in a fume hood, because there's a lot of stuff that, you know, you open the bottle and it's just going to kind of go into the gas phase relatively easy. You don't want to smell all that stuff, so you usually do a lot of the work. Oftentimes when you're dealing with organic stuff inside a fume hood. Inorganic compounds like salt and so forth are ionic and usually are soluble in water. Again, they're able to interact well with water because they are positive and negatively charged. Water, again, has a positive side and negative side, so they interact really well. You really don't, again, get that with something like our organic guy here, like propane, which is right there. Here's just a table from your book of some of the differences between organic and inorganic. Major differences, you know, are sort of melting points and boiling points, kind of opposite ends of the spectrum. Also in terms of flammability. And again, in terms of the actual bonding that's happening, organic pretty much sharing electrons, obviously ionic, no sharing of electrons, held together by really an intramolecular force, that electrostatic attraction. Any questions on that there? Identify each characteristic as typical of compounds that are inorganic or organic. So take a second and see what you come up with there. Okay, let's take a look. So if it has a high melting point, we would expect that to be inorganic. Again, held together very tightly, so that obviously affects things like not soluble water would be organic, right? Again, non-polar versus polar for water. That's pretty much all carbons and hydrogens, which is pretty much a hallmark of organic sort of molecules. Magnesium chloride, that's a metal and a non-metal, right? So that is basically an ionic compound, which would be inorganic. Easily burns of air, that is our organic, yes, combustion reaction, right? Remember, organic combustion, a little bit of oxygen, you make CO2 and water pretty much all the time there, along with obviously an organic guy to start with the oxygen. Has covalent bonds, that is again going to be typically our organic guy, carbons, hydrogens, nitrogens, oxygens, that's all non-metal interaction occurring. Any questions on any of those there? So let's talk a little bit about some of these organic guys. Sometimes certain organic compounds are referred to as hydrocarbons. Hydrocarbons, much like the name implies, is basically a compound that's made up of two elements, is made up of carbons and hydrogens. And basically the connection is like we talked about there, it's always sort of the backbone of all carbon molecules is really the carbon to carbon connection. And again, hydrogen always on the outside there attached to the carbon. Just like we talked about with bonding, we would never ever find a hydrogen like in the middle. Why do we not find hydrogen in the middle? It has too many bonds, right? It should only have 2 electrons. Still in organic compounds should still only have 2 electrons, which means just like we talked about in bonding, never in the middle, hydrogen always on the outside. Always usually found itself attached to a carbon in most cases, can be attached to other things like oxygen, but a lot of times strictly to the carbon. In organic molecules, the basis and the very important thing to remember as we go through these chapters and you're drawing things is about bonding, and carbons really need to get to 4 bonds. So carbon does need to complete the octet rule. It needs to get to 4 bonds, and it typically in organic molecules has 4 bonds. By the way, it does not have more than 4 bonds, and you want to watch yourself, because when people start drawing these things, before you know it, there's like 4 million bonds to carbon, and they just keep on adding and so forth. So don't want to do that. So carbon should always get itself basically to 4 bonds in an organic compound, and never should have more than 4 bonds. Otherwise, it will be definitely wrong. Now, there are certain hydrocarbons which are referred to as being saturated. Saturated basically means that the carbon has the maximum number of hydrogens that it can have. So saturated basically means that it has the maximum number of hydrogens per carbon. And really where that happens is, as it's here, at a compound that basically has only single bonds. So it all can have only single bonds. The other thing with sort of drawing pictures, as we'll talk about, is, you know, if you're sort of out of all other elements and you need to put it on your picture, everything else is basically hydrogen to get carbon to 8 bonds, basically. Not 8 bonds, 4 bonds, 8 electrons. So you basically add carbon in here. So when we look at each of these carbons, this is a saturated hydrocarbon because this carbon on either side, it obviously uses up a bond between the 2 carbons. So that's 1 bond. And then it completes its need for 4 bonds by having 3 hydrogens to each of the carbons there. So the guy on the right has 4 bonds, the 3 circled hydrogens, and obviously the 1 it is there between the 2 carbons. And the guy on the left also has the maximum number of hydrogens that you could have. Later, we will talk about unsaturated hydrocarbons, or unsaturated. And basically unsaturated means the opposite, as we will see. It basically means they don't have the maximum number of bonds. So how does that occur? Where if we just kind of look at like something like this, and we have all hydrogens. Let's say, for example, I needed to double bond the carbon in the middle. So if I just put a line there in the middle, is that good in terms of bonding? It is not, because the carbon on the right has how many electrons? It has 2, 4, 6, 8, and 10. Too many, right? Octet rule. Carbon on the left also would have 2, 4, 6, 8, 10. So when we make a double bond, or really in any case, when you put on a double bond or even a triple bond in an organic compound between 2 carbons, what ends up happening is you basically sacrifice a hydrogen on each carbon to allow you to do that. So hydrogen over here goes away to allow us now for each carbon to have just 8 electrons, and everybody's happy. So everybody still meets octet rule. Octet rule, I'll spit that out right, I think. Now, you know, for example, if we need a triple bond, as we will talk about later on, that also, if we went to triple bond there, if I could get something to triple bond with here, try that again. All right, triple bond. Again, we'd be in the same situation if we just did it like that. We would again be basically too many. So basically, a good thing to remember in organic chemistry is every time you slap down another line, you should lose a couple of hydrogens. One on each carbon basically is what occurs in that particular case. What I just drew here, what I had up there before that, those are considered, as we'll talk about, unsaturated hydrocarbons. They have at least a double bond or a triple bond sort of thing occurring. And again, the result of a double bond means each carbon is going to lose 2 hydrogens. Triple bond, we're going to lose 2 more. The result of that is they will now not have the maximum number of hydrogens that they could have. And that's, again, why they're considered unsaturated versus everybody that is single bonded will end up with the maximum number of hydrogens in that particular case. And that's what's referred to as being saturated. Any questions on that there? So here is a look at a carbon compound. This is pretty much your simplest organic compound you could have. And that is CH4, which is methane. Basically 1 carbon and 4 hydrogens. And here's a few different ways to look at it. We have our space-filled model, ball and stick model, like if you built it. Our wedge model, where we have kind of a wedge coming out, the dashed line kind of going back in 3-dimensional space. Here's just our sort of expanded structural formula. Expanded structural formula is pretty much we draw out all the bonds, almost like a Lewis structure, showing all the bonds to the hydrogen is basically what that is. There's also the condensed formula where we basically don't draw out the hydrogens. So those are 2 very common, unless you're doing computer modeling or you're making stick figures with the model kit, you probably won't see too much of A and B or have to do much of A and B. Personally, I'm not going to ask you to do C, which is 3-dimensional space drawings or anything like that. So for us, these are 2 of the 3 really main type of structures that we come across. Expanded basically is kind of like what I drew out a second ago as well before I started making some double bonds. This is an expanded structural formula. Again, it shows basically all the bonds to hydrogen. If we were going to do a condensed formula of this, basically we just take the parts and we could start here, and that's a carbon with 3 hydrogens. So we would write CH3 dash, and on the other side, a carbon and 3 hydrogens. CH3, this would be the condensed formula in this particular case. Any questions on that there? And obviously the molecular formula is just like molecular formulas we talked about before. A molecular formula, would just say like C2H6 would be the molecular formula. Obviously the molecular formula basically just tells you what's there. Structural formula, which is the top one, gives you a lot of information about obviously how everybody's connected together. Condensed formula, oftentimes we draw what is used to be called the condensed structural formula, where it kind of shows where everybody's kind of connected and stuff like that, without the hydrogens being drawn. So here's ethane, which is the second organic compound you could have, C2H6. And again, here we see our expanded structural formula, and again, our condensed formula there as we kind of look at it. Now, when we look at the shape of this, right, around each of the carbon atoms, let's take a look at this one first. Just like we did with geometry, right, we would count the number of electron pairs. This guy, carbon, has how many electron pairs in this one? It has 1 electron pair, 2 electron pairs, 3 electron pairs, and we still count this one, which would be 4 electron pairs. So it has 4 electron pairs. It also has 4 bonds. The molecular geometry for somebody with 4 electron pairs and 4 bonds is tetrahedral. So if you remember, tetrahedral has a bond angle of 109.5 degrees is the bond angle associated with tetrahedral. By the way, every single one here has the exact same geometry, right? This guy's got 1, 2, 3, 4. This guy's got 1, 2, 3, 4. This one has 1, 2, 3, and 4 electron pairs and bonds for each of them. When you have multiple carbons, you basically just put your hand over the other part and look at each carbon separately. So they all have that tetrahedral arrangement. And again, this would be the structural formula here. If we were to write the condensed formula, it would again be CH3. And again, we can break it up by just looking at here. So that is CH3, then here CH2, CH2, and CH3 in this case. So CH2, CH2, and CH3. This would obviously be the condensed formula. Now, there's a third type of formula that we commonly see, and it is also what is referred to as line structure. And basically, it is what it sounds like. It's just lines. You don't write anything else but lines, basically, in the most case. And if we were to do the line structure for this guy, it would look just like that. And that would be the line structure here. So let me show you what each of that represents. So everywhere there is sort of a point or where a line ends, it's assumed to be a carbon. That would be a carbon, that would be a carbon, that would be a carbon, and that would be the carbon. As you can see, that would be the 4 carbons we got going on in the middle. And as we talked about, basically every carbon needs 4 bonds. And if there's nothing else written, it's assumed that there's also the correct amount of hydrogens there. So the guy at the end has 1 line coming in, which means he needs 3 hydrogens. Guy here has 2 lines coming in, 1 on each side, needs 2 hydrogens. Same thing with this guy, 2 lines coming in, needs 2 to get the 4. 1 line coming in, needs 3. So that is what a line structure basically represent. Usually you don't write obviously all the carbons and hydrogens there. It is sort of a very simplified sort of formula for an organic compound, where again, at each of those spots are basically carbon. This is also what is sometimes referred to as the zigzag sort of structure for these guys, and it's zigzag structure because each one is tetrahedral shaped. First guy goes tetrahedral, second guy goes tetrahedral. The result of that is you get these sort of structures that end up being this sort of zigzag shape that occurs because of the tetrahedral geometry. Any questions on that there? So those 3 are 3 very common structures that we see in organic chemistry. Definitely structural formula, condensed, and line structure, you know, does pop up a lot. Any questions on that there? Okay. So let's talk about the first type of organic guys, which are alkanes. Alkanes are basically single bonded. Now, when we talk about different types of organic compounds, they mostly all have what are referred to as functional groups. And what are functional groups? Well, functional groups are pretty much the part of the molecule that makes it a specific type of organic compound. So typically speaking, for alkanes, the functional group is like simply the carbon-carbon single bond for the most part. That is basically what alkanes are. They have a general formula of CnH2n plus 2. So what does that mean? N is the number of carbons. So we saw methane a second ago. Methane has 1 carbon, which means N is equal to 1. 2 times 1 is 2, plus 2 is it should have 4 hydrogens, basically. We saw ethane, which had 2 carbons. 2 is N. 2 times 2 is 4, plus 2, it should have 6 hydrogens. So alkanes follow that simple formula of CnH2n plus 2, and that will get you basically the formula for all the alkanes. Alkanes are super important because every single name that you do in organic chemistry always finds themselves coming back to the alkanes, more specifically the first 10 alkanes is pretty much what everybody comes back to. So if you want to do well in organic chemistry, the faster you understand and learn the first 10 alkane names, the much better off you will be, because everything just references back to those names. So it's important to know the names, how many carbons, and the formulas for each of those things. The IUPAC is what is known as the International Union of Pure and Applied Chemistry. I'm sad and I know that, but those are like the three guys that sit in a room and decide how you are supposed to name everything and who decides what the name of the elements are. So you could thank those guys and probably girls as well in terms of coming up with all the names involved. So alkanes are hydrocarbons that contain basically carbon and carbon, carbon hydrogen bond. They're formed by a continuous chain of carbon atoms. The IUPAC way of naming is they end in ANE. We use some Greek prefixes once we get to sort of 5. So when we talk about sort of the structure of organic compounds, there's sort of a continuous straight chain, is sometimes called. And basically what that means is essentially all the carbons, obviously with some hydrogens, head off in a straight chain. As we will see, there's also branch chains. And those guys, much like branches on a tree, is on a tree, you have the main sort of spot, right? And every so often you got some branches kind of coming off in other directions. So that's what's referred to as a branch chain. So let's talk about those first 10 alkanes, their formulas and their names. And again, really important to get those guys down. So let's start with the first 10 alkanes. All right, number 1, again, all these will follow this formula, CnH2n plus 2. We have our 1 carbon, which means you have 4 hydrogens. That is methane. We have 2 carbons. Again, 2 times 2 is 4 plus 2, which is 6. That is known as ethane. When we get the 3 carbons, 3 times 2 is 6 plus 2 is 8 on this side. That is how many hydrogens we should have. That is propane. 4 carbons, 4 times 2 is 8 plus 2 is 10. That is butane. 5 carbons, 5 times 2 is 10 plus 2 is 12. That is pentane. 6 carbons, 6 times 2 is 12 plus 2 is 14. That is hexane. 7 carbons, that would have 14 plus 2 is 16 hydrogens. That is heptane. 8 carbons, 8 times 2 is 16 plus 2 is 18, would be octane. 9 carbons, 9 times 2 is 18 plus 2 is 20, would be nonane. And lastly, C10, and that is 10 times 2 is 20 plus 2 is a 22. That is decane. Really, really important here to know these guys for sure. Everything, again, is going to reference back to this list of 10 and every sort of organic compound that we come across. The importance to know is exactly this, the name and how many carbons are associated with that name. That is the most important thing. As we talk about really naming things, it's all about how many carbons. So you're going to find how many carbons. It will probably match somebody on this list. We'll do a little bit of tweaking to the name, but that is where the basis of the names pretty much come from, is these 10 here. Any questions on that? All 10 of these guys are the same sort of connection. It is all the carbons attached to the carbons, and then obviously the hydrogens attached to it. So if we looked at pentane, which is 5, it is attached carbon to carbon. And again, the hydrogens there would be attached to the carbons, giving carbon 4 total bonds. What I am drawing would be what is the structural formula. And again, that is our C5H12. You could write our CH3, CH2, 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 CH3, which would be our condensed formula. And again, this coming to here. This coming to here, this to here, this to here, and this to here. Lastly, obviously, we can have our line, which would be look something like this, like a mountain range, basically. But again, although you don't put the dots, this would be 1 carbon, 2 carbons, 3 carbons, 4 carbons, and 5 carbons. And again, each of those carbons would be assumed to have the correct number of hydrogens, again, to get carbon to its magic number of 4. Yes. So this would be our line structure. And just the molecular formula would be what we have right here. Any questions on any of those there? Okay. And again, typically in line structures, you don't put the little circles, but that's just to show you what the carbons are. Yeah.
The line has always 4 carbons.
No, the line structure is basically just this guy. But at the idea, and you want to always remember this, is carbon basically needs to get to 4 bonds. So if there's nothing else there and you need to figure out what else is there besides the carbon, it's hydrogens to get carbon to 4 bonds. So that's why when we look at this guy, you go, okay, I know that's a carbon, but there's nothing else drawn there. When we look at that guy at the end, we could see that it has 1 bond coming into this carbon here, which means basically a short 3 bonds, right? And those 3 bonds, although never shown in the line structure, those 3 bonds are basically hydrogen. And it has the 3 hydrogens, which would be this hydrogen, and that hydrogen. That gets carbon to 4 bonds. Just like the guy right here has 1 line coming in, 2 lines coming in. He's got 2 already, which means to get him to 4, he only needs 2 more. And those would be assumed to be the 2 hydrogens that we would see 1 and 2 right there. So those would be the 2. Yeah. So it's really important to remember, as I said earlier, that carbon basically needs to always have 4 bonds in this situation, never more for sure, never put more. And if you sort of are drawing things, and when we get into that, you know, when you're out of everything else and you need to kind of finish your structure, it's basically just hydrogens. You're just going to put the appropriate number of hydrogens to get each carbon basically to 4. And that might mean a carbon needs 3, might mean a carbon needs 2, might mean a carbon needs 1 hydrogen to get there, or it may mean that a carbon actually doesn't need any hydrogen. So those are your options. But we kind of use hydrogen. You can think about it as a way to get carbon to 4, basically. Other questions? Any other questions on that? Yeah. Good. Yeah. Okay. What did I do? like there's slides. Here's a table from your book that has, again, what we just went over. And again, over here, although that's these are off, by the way, at least on this slide. I don't know how it is in your actual your book. This is actually the line formula for here. They're off by 1 on this slide. I don't know if the table is like that as well in your book or not, but they're basically off by 1. There really is no line formula for methane because there's just 1 carbon. So, nobody does a line structure for it. But yeah, so on this, they're kind of off by 1. But here's the line structure on the right, condensed formula, molecular formula, and then obviously the name. So really, really important to make sure you get a handle on those guys as soon as possible. So as I mentioned, the condensed formula is basically a place where we just basically don't draw out the hydrogen bonds. Most people these days do the lines though, between the kind of CH3, CH2 and stuff. And that's why it used to be called sort of the condensed structural formula, because you have the lines. Technically speaking, without the lines, it's just condensed formula, no lines between them. But it is important to remember that although it is written like this, the connection that's actually happening is always carbon to carbon here, and then obviously the hydrogens off of those carbons. So it may imply, if you kind of look at that formula, that the hydrogen is attached to the carbon, and the hydrogens are in the middle, but it's not. It's always carbon to carbon connection, and again, hydrogens on the outside, like we talked about. So here's the differences as we talked about: expanded, draw out the hydrogens; condensed, not really draw out the hydrogens. And then obviously our expanded and our condensed formulas there. Molecular formula, looks like your book may call it just line structure, line angle formula. And again, in typical line structure, we don't write these guys in. They're just showing you what's at the end of those lines, as we talked about. And again, if you had this like a lonely line written like that, people oftentimes go, all right, well, like what's at the end of it? And it's the same thing, even though it's pointing up, it would be assumed that carbon would be there. And obviously it only has 1 line going up. So it would need 3 hydrogens attached to it. So it's what's known as a methyl group. If you ever have a line structure and there is a line and they want it to be something other than carbon, they will write it there. So you would have something like Br, and that is a bromine attached to it. So in line structure, if there's nothing really there, it's carbons and hydrogens. If it's going to be something else there, they will actually draw it in and you'll see it. So for example, you had a double bonded oxygen, they would draw it in on the line structure. So again, if it's something other than carbon hydrogens, it would be technically kind of drawn in a lot of times, even on line structure, but carbon and hydrogen is not really drawn in, are written into the structure. Any questions on that? So again, as I mentioned, these are really the 3 sort of formulas that we do use a lot. Again, ball and stick is really what you do when you kind of build models and stuff like that. So here's just some examples of butane and different ways of writing it. This is expanded structural. These are all condensed structural formulas. Now you may say, are all these things different things? And the answer is no, they are not. So one important lesson, especially when we talk about things like isomers and stuff like that, is pretty much when you go to name something, the most important thing that you're looking for is the longest continuous carbon chain. What that means is you start on one side and you continue down the carbons until you hit like a dead end. You can't go backwards or anything like that. Doesn't mean it's always got to be the straightest. You could go this way and go up and over. You just can't back up and go a different way. So you kind of go one way until you hit a dead end. You could even go like down and back up and over, as long as you don't back it up or anything like that. So the reason why all these, you may think there may be different compounds, they're really not, because if we just did that, that's 1 carbon, 2 carbons, 3 carbons, 4 carbons, I hit a dead end, and that is butane, basically. Nothing else is there. Even though this may look different, it is still ultimately 1 carbon, 2 carbons, 3 carbons, 4 carbons. I never stopped right until I hit a dead end. This guy, 1 carbon, 2 carbons, 3 carbons, 4 carbons, 1 carbon, 2 carbons, 3 carbons, 4 carbons. These are all just a chain of 4 carbons, happen to be drawn differently, but they all are 1, 2, 3, and 4 carbons. They're all 4 carbons in a row, nothing else there. They're all basically representations of butane. Are any of them wrong and drawn like that? They are not. Most of the time people would just draw the condensed formula like the first one, but technically the other ones are the exact same thing. So sometimes people, in a very important lesson to understand when you're looking at organic compounds and especially structures of them, just because it looks different doesn't necessarily mean it is actually a different compound. It may just be drawn differently. And one way that you could definitely tell whether or not something is the same compound or something different is to actually name it. You end up with the same name, it's the same compound. You end up with a different name, it's 2 different compounds, and we'll see some of that as well. And again, same thing here. You know, we started up sort of with the line structure. Here we kind of started down and then coming up. But again, ultimately, they all have basically 4 spots there when you look at it. Again, 1, 2, 3, and 4. 1, 2, 3, and 4, basically. So it's all 4 carbons in a row. Any questions on that there? Okay. All right, so why don't you take a second and do A, B, and C here on that? And while we're at it, why don't you also do the line structure as well? Okay, let's take a look. Let's just start with the name actually. So we got 1 carbon, 2 carbons, 3 carbons, 4 carbons, and 5 carbons. So we got 5 carbons. We also could count the hydrogens there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So really the 5 carbons is all we need for the name. 5 carbons is pentane. By the way, these are alkanes and they all end in ANE, right? So that is basically how a lot of the naming is. Alkanes always end in ANE, like the name. Condensed formula would be basically just breaking these apart. So that is a carbon and 3 hydrogens. That is a carbon and 2 hydrogens. That is also a carbon and 2 hydrogens. 1 more carbon and 2 hydrogens. And lastly, a carbon and 3 hydrogens. So that would be the condensed formula. That would obviously be the name. That would be our formula and our line structure. Again, we would just basically zigzag until we get 5 kind of points, if you will. So 1, 2, 3, 4, 5, that would be our line structure there. Any questions on any of those there? So ethane, again, would be 2 carbons. So that is C2H6. And the condensed formula would be CH3 and CH3 would be our condensed formula here. Heptane is 7. So that would be C7. And again, if you're not sure, you could use this formula. So 7 times 2 is 14 plus 2 means it should have 16 hydrogens. And it would be, if you're not sure, you could actually just start with the carbons. 1, 2, 3, 4, 5, and 6. And you basically just look at what we talked about. The guy at the end has 1 line, which means he needs 3 hydrogens. The next guy over has 2 lines. To get the 4, he needs 2. Guy in the middle here also has 2 lines. To get the 4, he needs 2. Next guy, same deal, needs 2. Next guy, same deal, needs 2. Needs 2. And the guy at the end has 1 line, which means he needs 3 hydrogens. So you could kind of do that as well. It's a really good way when you're drawing things to start with just the carbons and kind of fill in the hydrogens and everything else. It's a really good way of doing that. Any questions on that there? Okay. Yeah. It is heptane, yeah. That's just a general formula for alkanes. So if you know how many carbons there are, but wasn't sure how many hydrogens, you could use that to figure out how many hydrogens, where the number of carbons is basically N. Yeah. So like on the last one there, N is 7. So 2 times 7 is 14 plus 2 is our 16 hydrogens that we would have. Other questions? Now, not all alkanes are sort of a straight chain structure. Sometimes they are what are sometimes referred to as a ring structure. And a ring structure basically just means that the ends kind of just close in on each other and make a structure. So we name these guys as basically cycloalkanes. They actually have a formula of CnH2 times N. No +2 on this one. The reason there is no +2 is when you close the ends of the chain together to make that bond, as we talked about earlier, every time you make a bond, you lose how many hydrogens? 2, and that's where the 2 went. No 2 on this one. So if we look here at propane, which is this guy right here, CH3, CH2, CH3, that has 3, 6, 8 hydrogens. Cyclopropane basically comes together and makes a triangle where each one is a carbon. And because it wraps together basically to make that extra bond, we lose the 2 hydrogens because each carbon in this case has 2 lines coming in, which means each one has only a need for 2 hydrogens, which gives us actually 6 total hydrogens in this case. Cycloalkanes are named the same way as alkanes, except you put cyclo in front of it. So instead of propane, you still count the carbons. 1, 2, 3 becomes cyclopropane is basically how you would name that. Cycloalkanes are pretty much our geometrical shapes. That would be the simplest you could have, which is your triangle, also known as cyclopropane. You could have your square. Square has how many carbons? 4, right? 4 carbons is butane. This would be then known as cyclobutane, obviously without the carbons drawn there. We then have our other shapes very commonly. That is 5 carbons, which would be cyclopentane. I'll get out of the way. And then we have this guy here, which has 1, 2, 3, 4, 5, and 6 carbons. 6 carbons is hexane. That would be cyclohexane in that case. So you basically just put cyclo in front of the name, but each one will have basically 2 less hydrogens than the straight chain. And again, that's the result basically of the carbons coming into each other and making that bond. Not really a double bond, but still making an extra bond that we don't see in there. And again, most of these are sort of drawn in line structure as just sort of shapes. So if you see shapes, it's some type of cycloalkane. Any questions on that there? And again, here's our, again, as I just drew, our triangle, our square, and so forth. And these are our popular cycloalkanes. This, by the way, would be the condensed structure for those guys where you would actually just write like CH2s all the way around in there. And then, so that's usually the way that you would see those two. All right. And that is obviously from your book as well. All right, so give it a name for each of these, see what you come up with. Okay, let's take a look. Count carbons. So 3 carbons, 4 carbons, 5 carbons, 6 carbons, 7 carbons, and 8 carbons. I don't see anything else drawn there, which means there's nothing else attached. They're all single bonded. By the way, in line structure, if you had more than one bond, it would be drawn in as well. So that'd be like a double bond as well. That would be like a triple bond if you kind of drew it in. So clearly I don't see extra bonds in there. So I know they're all single bonded and alkane. And I counted 8, I think. So that should be octane, A-N-E at the end of that one. Any questions on that one there? Same thing here, just going to count carbons. So that's 1, 2, 3, 4, and 5. So 5 is pentane. Difference though here is one of those shapes and it's a ring type structure. So we put the cyclo in front of it and this would be cyclopentane. Any question on either of those two? Okay. All right. So give these guys a go. All right. So again, longest continuous carbon chain, always where you want to start with. So this is pretty straightforward. It just goes right across. So 1, 2, 3, and 4. This is obviously condensed formula here. Nothing else there but hydrogens and the carbons. And 4 would be butane. This is our guy we saw earlier, 1, 2, and 3, which is propane, again in a ring type structure, has 2 less hydrogens and becomes cyclopropane. Same thing here, just go straight across in this condensed formula, 1, 2, 3, 4, 5, 6, 7, and 8. So that is our octane. And lastly here, 1, 2, 3, 4, 5, and 6. Again, 6 is hexane. We once again see this sort of shape or ring type structure here that gets the cyclo in front of it, and this would be cyclohexane. Any questions on any of those names? Okay, then let's talk about naming stuff that has other things attached to it. It makes it a little bit more interesting, I suppose. So when an alkane has 4 or more carbons, the atoms can be arranged side by side, or a group that's called a substituent. So if we look at each of these things here, we basically have the exact same number of elements that are present. So for example, let me just write this one bigger here. We have CH3, CH2, CH2, and CH3. Here we have CH3, CH, CH3, and a CH3 this way. Top guy has 1, 2, 3, 4 carbons and 10 hydrogens. Bottom guy has 1, 2, 3, 4 carbons and 10 hydrogens. They both have exactly the exact same molecular formula. So again, we're going to talk about, are they the same thing? So let's talk about, are they the same thing? We're going to talk about really naming. So when you go to name something, the very first thing that you want to do is the longest continuous carbon chain. So let's do that in each of these cases and sort of see what we got going on. This guy should be pretty easy to see. It is just straight across. So that is 4, right? Longest continuous carbon chain in the bottom is how many? It is actually only 3. And you could get that by going straight across. I hit a dead end, right? I could actually go this way and up, right? Will give me 3. You could actually, if you want to go, it's basically the same, but down and over. So there's a couple of different ways you could actually get 3. And when there is actually multiple ways you could get the same number, does it matter which way you go? The answer is no, it doesn't. But a lot of times it's easier just to take the straightest one because you can kind of see it. So why is the straightest one important? Well, the straightest one is important because that is basically the base of our name. So let's start with this guy. 4 carbons in a row is going to be what name? It is going to be butane in here. There's absolutely nothing else attached there. The main chain is the whole thing, right? If I circle my highlighted guy, which has only 3 carbons attached, 3 carbons is which name? 3 carbons is propane. That is the base of that name, which is actually propane. When I look at what I highlighted and I circled, that is what I call like the base of your name, the main chain. This is what we like to call a branch because off of that main chain, there's still something hanging out there that is not part of the main chain, but like a tree, branch that's hanging off of it, and that is the guy that's up on top. Everybody see that? Yeah. Now, that also has a name, but that is what is considered a substituent, which is a fancy way of saying it's basically a group that's attached. And would you believe it or not, a carbon-based group is what is referred to as an alkyl group. Now, that group that's attached is also based off of the first 10 alkanes. So which of the first 10 alkanes has one carbon? Alkyl group is the guy circled in red. It's basically a carbon containing part of the main chain of the compound. So that is what is referred to as an alkyl group, and it's basically a carbon-based group, and is based off of the first 10 alkanes. So if I just draw that, that is CH3, what's up on top, right? That is what we got up there on top. That has one carbon. One carbon is methane, right? But what is methane's formula? It is CH4. That is CH3. It is not exactly methane, because with methane, if I drew methane and I wanted to attach methane to another carbon chain, can I attach it just like that? I cannot, because now this carbon has too many bonds. So what an alkyl group is, or a group like this is basically one of those alkanes that is missing a hydrogen. And it's missing a hydrogen because then it's able to actually attach, because if I take a hydrogen away from methane, like we'll take this guy, now when it attaches, that carbon is good, actually. It now has 4 bonds, which is what it needs. So alkyl groups are groups that are, and they're sometimes referred to as substituents. These are groups that are attached to the main chain of the compound, but are missing basically one hydrogen that allows it to attach, so it doesn't end up with more bonds. So it is still named based off of methane. Clearly, we cannot call it methane because that has 4 carbons. This is what type of group? This is an alkyl group, which ends in a YL, which means we get rid of the last part of methane. And this is what is known as a methyl group. So the group here is named based off of those alkanes. Drop the last part, put YL on it. So that is a methyl group. So I'm just going to redraw it here so we can kind of go through it one more time here. So CH3, CH3, CH3. So again, this part here, propane. This is our group that's attached, which is known as a methyl group because it has 1 carbon. Any questions so far?
So the methyl, it would be in front of it would be methyl propane.
So we're going to get to the rest of the names right now. Yeah. Other questions? Okay, so organic chemistry naming, it's all about location, 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 basically telling everybody where things are located. The basis of the location is actually the longest carbon chain. So if we look at our longest carbon chain, that's the guy in the box. We could actually number the carbons, and you have 2 ways of numbering. You could go right to left, where this would be carbon 1, that would be carbon 2, and that would be carbon 3. Your other option would be, if you went the other way, this would be carbon 1, this would be carbon 2, this would be carbon 3. We want to give the location to the group that's attached. And with alkanes, the location is always whichever way is the smaller number. So the priority in terms of numbering goes to the groups that are attached, and we want to give that group the smallest number. In this case, does it make a difference which way we go? It doesn't, and that sometimes happens. You could go left to right, right to left, and that group ends up at the same number. But if you went left to right and the group ended up at like 2, and you went right to left and the group ended up at 5, you would want to go the way that it ended up with 2. Once you determine which way you number, you got to stick with it for everybody that's there. But in this case, there's just a methyl. So to answer your question, this would end up being called 2-methyl propane. Propane, the longest carbon chain. Methyl, the group that's attached to it. And 2 is the number of on the carbon chain where you can find that methyl group. It is hanging out right there at carbon number 2 in this case. First off, any questions on there? Now, first off, if you remember the other thing that we had up there, which was this guy. Now that we have the correct name, that is butane. That is 2-methylpropane. Are those guys the same compound? They are not. They actually have 2 different names. So that makes them different compounds. That actually makes them what are known as isomers. Isomers are 2 things that have the exact same molecular formula. So if you remember, they both have 4 carbons and 10 hydrogens, but different connectivity, which gives them different names and different properties. Yes. That's this guy right here. Yep. Now, yeah. Longest continuous carbon chains. That's always where you want to start. Longest continuous carbon chain. Again, it might not always be the straightest. You could go up and over. The only thing you can't do is backtrack. So if you go one way, you got to go until you hit a dead end. You just can't go back and keep counting. So you do want to try multiple ways, because sometimes you're surprised, like, oh, there's like a weird hidden way that's actually more carbon. So you want to try all your options, you know, start at all places and hit the end. And whichever one is the longest continuous carbon chain, it should match one of those 10 alkanes, and that would be the base of your name. Yeah. And that's why in this one here, the continuous carbon chain was 1, 2, 3, and 4 in a row. And that's why it's propane. Nothing else was attached. That's all part of the whole chain, basically. Other questions on that? Yeah. Yeah, methyl is actually the group that is not part of the longest continuous chain, but is attached to it. So anything that's not technically like in the box of the longest continuous carbon chain becomes a group. And a lot of those groups are based off of the first 10 alkanes, where it's missing 1 hydrogen, and you change it from the alkane name to add the YL. So methane became a methyl group. If I had a 2 carbon group, it would go from ethane to a ethyl group. Had a 3 carbon group, it would go from propane to a propyl group. So, you know, if I had, you know, something like this, I won't finish the whole thing, but we'll say that it was our group. That would be a ethyl group, as it's based off of 2 carbons, you know, and so forth, as you find there. Now let's talk a little bit more about sort of this naming. So longest carbon chain, you want to kind of box it, is a good way of doing it. Everything that's outside of your box is going to be some type of group. You want to give the group the appropriate name, like I just talked about, by dropping the ANE, putting the YL. You want to number the longest chain, which would be in your box, whichever way, one way or the other. The way you determine which way you should number is whichever way gives the group the smaller number is the way that you should go. So whichever way gives the group the smaller number.
I don't understand that when you say.
So we'll see an example in just a second, and then we'll see. And then you basically need to name it. The last couple of things is you always use a dash between a number and a letter, which is why we have a dash here between the 2 and the M, right? And you use a comma between 2 numbers. So between 2 numbers, if you get it, you want to use a comma. So what's that? When you ask to name them, they're asking, yeah. Why don't we do this, and then we'll name everything, and then we'll go through the naming process. How's that? That'll probably cover both questions, I think. Okay. So isomers, like I said, are basically the same molecular structure, but different ways that they are connected. So let's start with the simplest way, which is if I want to do 5 carbons in a row, it's a good way of starting it. So just 5 carbons. Now everything else here will be hydrogens to get the carbon to 4 bonds. So this would be an isomer here. We'll get to the name in just a second here of these guys. Now, let me say maybe I don't do 5 carbons in a row, but I decide let me do just 4 carbons in a row with maybe a carbon up this way. And I put in my hydrogens. And again, I'm putting in hydrogens to get carbon to 4 bonds. So that's how many hydrogens I'm putting in. Let's say I didn't do 4 carbons in a row, but I only did 3 maybe in a row. And I put one here and one here. Now I put my hydrogens in. And that's 3. So let me just draw this one here for fun, maybe. Actually, I have to do this. Okay, so I drew here 4 structures. The idea when you're going to draw isomers is basically just keep the carbons attached to the carbons and kind of arrange and move them around and see if you actually ended up with some different thing. If I didn't screw up here, I should have in every structure 5 carbons and 12 hydrogens, basically, which I think I do. So let us do the naming of each of these. And this is really going to help us determine, did we draw isomers or did we just like draw the same thing and just kind of looks different? So let us start with the first one, which is always you want to try to find your longest carbon chain. So we'll start here. The first one I drew, longest carbon chain is, and this first one, 1, 2, 3, 4, and 5. Yes. The base of the name is going to be based off of that. So something with 5 carbons is pentane. Is there anything else attached besides hydrogen here? There's not. So this is basically it. Everything is part of the longest continuous chain, and that would be the name in this particular case. There's nothing else there other than hydrogen, obviously. So you got to have something other than hydrogen attached there to have a group, coming off of it and stuff like that. Let us go down to this guy here. We'll still go to our first step since we didn't get past our first step on this first one. Longest continuous carbon chain here is how many? It is 4, and you could get that by going this way, straight across. You could also get it, by the way, going this way, 1, 2, 3, and up is 4. So you could do that. It doesn't really matter which one you choose. You could do either one. I personally think that, if you have the option for like the straight move, it's probably easier to see for most people. Now, this has only 4 carbons as the longest carbon chain. That means the base of this name would be what? It would be butane. And because of that, we actually have this guy that is hanging off of that group, right? Off of that chain. And because it's not part of the main chain, it is now a group. And that basically is also based off of the first 10. That group has how many carbons? That is 1, which is based off of methane. Because it's a group, it becomes a methyl group. So that is what this is. That is a methyl. So I think we're going to get to your question, I think, next, I believe. So now we come to longest chain, find groups. Now we come to kind of an important part, which is numbering the chain. So we want to number the chain. And then in this case, there's really two options to number the chain. We could go left to right, which means this would be carbon 1. This would be carbon 2. This would be carbon 3. This would be carbon 4. Our other option is to number the opposite way, which means that this is carbon 1, that is carbon 2, that is carbon 3, that is carbon 4. When you number the chain, you want to number whichever way gives the group the smaller number. So going in the green direction, my group is at what carbon? Right. Going in the black direction, my group is in 2. Which one's smaller? Yeah, the bottom one. So this is the way that we would want to number going left to right in this case, because that gives the group the priority and the smaller number, which I think was your question, yes? So that's what we mean by giving the group the smaller number. So what we want to do is once we determine that, we want to get rid of the other numbering. And we want to number this way. So now our group is at carbon number 2. So basically what we need to tell people is that's where you find that group. So that is where the 2 comes from. And we need a dash because it's between a number and a letter. The proper name for this guy on the left would be 2-methyl butane. First off, any questions on that naming there? Secondly, first off, are these 2 isomers of each other then? Do they have the same name or different names? They have different names, but they all have the same amount of carbons and hydrogens, right? So they are isomers of each other. And we know they are different because they have different names. Any questions so far on that? Yeah.
So if the group was in the fourth one, would it be 4-methyl butane?
No, if the group was on the 4th one, it probably would actually be part of the longest chain. So
Oh.
yeah. Yeah, because technically speaking, it is located at carbon number 2 is where this methyl group is located. That's where it's attached to the chain. Yeah. Yeah. So you're talking about this guy right here, right?
Yeah, I'm just saying if it changed from where the other group is attached from, does it change the number in the front?
Yeah, we're gonna we'll name the guy on top, and I think that will probably answer your question. I think if you're asking about, kind of like this situation up here. But let's do the guy on the bottom first, and before we get to that guy. Longest carbon chain on the guy on the bottom is? It is 3. You could get it multiple ways. You could go straight. You could go straight and then up. You could go straight then down. By the way, you could just go straight down the middle as well and get 3. No matter which way you go, 3 is a winner here. I'm going to go with just a straight across 3. So 3 carbons is what name? Propane. That is the base of the name here. Now, the next thing we want to do is identify our groups, which would be this group right here and this group right there. Let's start with this group. This group is 1 carbon, which means it's a methyl group. This group is also 1 carbon, which means it's a methyl group. I have 2 methyl groups in the same compound. When you have 2 or more of the same group in the same compound, doesn't have to be on the same carbon, but in the same compound, we actually use prefixes. So prefix for 2 is di. So this is known as dimethyl. The di is because there are 2 methyl groups in that compound. Again, they don't have to always be on the same carbon, but just that there are 2 in there. If you had 3 methyl groups, you would call it tri. If you had 4 methyl groups, it would be tetra. So we'd use kind of the same prefixes we use for like type 3 compounds type of thing. Now we still need to give locations of where these guys are because people need to know these things. So if we go left to right for our chain, this would be carbon 1, right? This would be carbon 2. This would be carbon 3. If I went right to left, this would be carbon 1. This would be carbon 2. This would be carbon 3. Doesn't make a difference in this case. It does not. So you go either way you want. They are both at carbon number 2. What makes a difference is they are both at the same carbon. You need to give the number twice. This would be 2,2 dash dimethyl propane. Remember I said comma between two numbers. There it is, yes. Dash between number and letter, or letter and number, however way you want to go on that. You need a dash between those things. So this is 2,2-dimethyl propane. If you work the name backwards, propane, longest carbon chain is 3. Dimethyl means there's 2 methyl groups in that carbon, and each of them are found at carbon number 2 and carbon number 2 in this case. That's what the name means. It's basically all about telling somebody where you can find everybody. Is that name different than the other 2? We had pentane, we had 2-methyl butane, and we had 2,2-dimethyl propane. Are those all 3 different names? Are they all 3 isomers then? They are, again, not just because they're different names. They're isomers because they also contain 5 carbons and 12 hydrogens, each of them. Yeah. So this is a very good way to determine whether or not you actually drew an isomer, or you just drew something that looked like an isomer. So let's take a look at the top one, which I think will answer the last question and determine us here. I'm just gonna, what am I gonna do? I'm gonna erase a couple of these things here. So I got somewhere to scribble on this page, I think. Get rid of these here. We'll go this way with it. All right, following our same rule here, right? Longest carbon chain on the guy on the right. It is 4. And again, you could get it a couple of ways. You could go straight across. You could also go straight across and then up towards the end there. We'll get you 4. 4 carbons means the base of this name is butane. Group that's attached would be this guy, which is a 1 carbon group, which is a methyl group. So that is methyl butane. Numbering this chain, going left to right. This would be carbon 1, that would be carbon 2, that would be carbon 3, that would be carbon 4. Going right to left, this would be carbon 1, this would be carbon 2, this would be carbon 3, this would be carbon 4. Going left to right, my group is at carbon number 3. Going right to left, my group is at carbon number 2, which is the proper way you should go. It should go this way in this case. So even though it is drawn differently, we're still going to go with the lower number, which in this case is actually 2-methyl butane. Is that a 4th isomer I drew? It is not, because that is also 2-methyl butane. These are the same name, even though they look different. It's just you turned the molecule around. That's all you did. And this would not be an isomer. So that's a really good way when you start drawing these things. Sometimes people think if I just draw it straight and then I just take the guy at the end and draw it down, or take the guy at the other end, draw it up, make it look cute, go up and over like a U, I drew something different. The really great way to check yourself is to name both of them. If you end up with different names and they both have the same number of carbons and hydrogens, you drew an isomer. If you end up with the same names and they have the same number of carbons and hydrogens, you drew the same thing over again. So it's a very common mistake when people are asked, hey, draw an isomer, they draw something like this, you know, like in the condensed form. And then they go, okay, cool, I'll just do like, that is definitely different. It looks different. But again, if you do the longest carbon chain, that is 4, and that is 4. That is the exact same thing. You just drew it differently. Even if you do get really creative and do something like this, which is very wrong. My CH2 should have been there. And then do that. There you go. This may look really different, but it is still 1, 2, 3, and 4. Still the same thing. So if you're not sure after you sort of rearrange things around, that's really what you want to do when you draw isomers, just kind of rearrange things around, connecting the carbons differently. Go ahead and name them. And again, if you end up with 2 different names, and again, they have the same number of carbon hydrogens, you're in good shape. But if you end up with the same name, you probably just kind of move something around incorrectly. Whew. I think that hit all the questions, I hope. Yes. Exactly. So right here at this carbon, you got 1 methyl and 2 methyls attached to it. You're welcome.